This is Charles 2, and this is my Physics 2212 Lab 4 on Faraday's Law. The purpose of today's lab is to observe the interactions between a falling magnet and a tube of aluminum foil. Some things to know beforehand are like magnetic flux, Faraday's Law, Lenz's Law, how to get the magnetic force, Newton's second law, Newton's third law. Today we'll be assuming that the system is the bar magnet and the surroundings is the aluminum foil and everything else. So experimental procedures is that we'll mark the north pole of the bar magnet. We'll then vertically align the aluminum tube and drop the magnet in with the north side going in first. We'll measure the time it takes to reach the bottom of the tube. We'll repeat for 5 trials. So for the initial conditions of our experiment, the aluminum foil had a length of 0.3 meters with a 0.05 meters and an inner radius of 0.02 meters. The magnet, on the other hand, had a mass of 0.023 kg, mu of 2.045. So what we can assume is that there will only be the only forces acting on this object is gravity and magnetic force, that we're dropping this magnet exactly at the center. So what would happen in a magnet, and how does this compare to a magnet falling in free space without a tube? The aluminum cylinder should slow down the falling magnet due to the magnetic force. So here's our data. As you can see on our experiment, the magnet had an average falling time of around 1.796 seconds. And now for the computational part of the code. Here is our initial conditions. You have the physical constants like mu over 4 pi, resistivity, and then the gravitational constant. And then down here we're initializing the conditions of our aluminum foil. We're still initializing like getting the aluminum foil, and down here we're creating the conditions for the bar magnet. Here is we're finding the magnetic field of a dipole using the Biot-Savart law, and then down here is the change in flux. And we're going to use these next two parts to calculate the magnetic force and the gravitational force. And then we get F net is just equal to F gravitational plus F magnetic. And then we use like Newton's second law to then get the velocity and position of the bar magnet. And from that, we can then calculate how much time it takes to fall through. And as you can see from our data, it only takes 0.316 seconds for the in a computational model for the bar magnet to fall through. So what if the resistivity of the conductor was reduced as close as possible to zero? How would the dynamics of the falling magnet change? Well, the magnitude of the current would increase because of the resistivity decreasing, and then because the magnitude of the current is increasing, the magnitude of the magnetic force will also increase. And because the only two forces acting on the bar magnet is gravity and magnetic force. If the magnetic force would increase, that means that it would fall down even slower. So what if holes or slots were cut into the tube? How would this affect the ring currents in your model? Well, the magnetic force would be weaker, and because, like before, the only forces acting upon the object would be magnetic force and gravitational force. If magnetic force would be weaker, then the magnet would of course fall faster. Thank you for watching my Physics 2212 lab video. I hope you had fun and enjoyed this video. Yes.